So I'm going to talk about well, rigorous function calculi for hybrid systems and beyond. And this is, by rigorous function calculi, I mean we're looking at not just intervals, numbers, but we want to look at functions as first-class objects. And the main motivation for this was the study of hybrid systems. And we'll see that hybrid systems are very rich boundary systems, and in particular, in order to study them, you really need to look at a lot of the fundamental operations in applied mathematics and mathematical analysis. And beyond, so to also look at potential applications beyond hybrid systems. So this work is joint work with a group of Tiziano Villa, who's, well, when we first started working on this project, he was at the University of Udine, and he's since moved to Verona, and two other members of this group, Luca Guerretti and Davide Bresolin, who's since moved to Bologna. These are a group in computer science, whereas I have more of a background in mathematics, so a lot of the function calculate stuff, this is stuff that I've been developing, whereas the hybrid systems applications are more of their work. So I'll start by motivating why I want to look at function calculi, which is to look at verification of hybrid systems. I'll then give you a brief review of the analogous calculus for real numbers, which I guess you're all familiar with, but if not, then feel free to ask any questions. And then go on to how we can generalize this to look at calculi of real value functions. I'll then say how we use this to analyze hybrid systems in our tool called Ariadne. So Ariadne, well, it's a reference, of course, to the legend of Theseus and the Minotaur and Ariadne. And Ariadne gave Theseus some string to try and find his way back through a maze. And we thought this was a nice analogy for trying to thread your way through the maze of possible trajectories of a hybrid system. And then also look at ideas beyond this, and especially I want to look at partial differential equations. So a hybrid system is, for me, a dynamical system in which you have continuous evolution, so you have a continuous state in some discrete mode or discrete location, which follows a differential equation until something happens, some guard condition becomes true, and at this time the state jumps to somewhere else, probably with a different discrete location with different dynamics. And to visualize this, you can think of, if we want to compute the evolution, what do we do? Well, we start from an initial point, or here a set of possible initial points, and then we have a continuous evolution, like this. And then here, here, and here, these are guard conditions. If we hit these conditions, something will happen. So we compute the evolution. Then we have to determine which points in the starting set will hit which guard condition first. And it could be, here we have a case where something may happen in this green area, but it doesn't have to. So a point that goes through here could jump in this green area, but could hit this blue guard here. So we figure out what's going to happen, we figure out when it happens. We then apply a reset. So this is just a map which says if we hit the guard here, then we jump to here. And then you continue evolving under the new dynamics in the new locations. So this is basically what a hybrid system does. And then the safety verification problem, which is the simplest verification problem, is to determine whether, given a set of initial sets and a set of safe sets, we always remain in the safe set if we start in the initial set. And because we want to do this rigorously, we want to actually prove that our system satisfies this, then of course we have to use rigorous numerical methods. And then if we want to do this for hybrid systems, well, we can see from the way we've described hybrid evolution, we can do this if we can do the following operations. So first, well, we need to compute the range of a function. We need to do this so we can test, for example, whether we hit our guard conditions. we need to compose functions. We compose functions in order to apply the resets. We need to compute the flow of a differential equation, so we need to solve differential equations. And also, we need to compute the times at which we hit these guard sets. So we need to solve algebraic equations. And usually the time will depend on the starting set. So we need to solve parameterized algebraic equations. And this is already, quite a large set of mathematical operations. And finally, if we want to test that our sets remain in some given set or intersect some given set, then it turns out we can express these as constraint satisfaction problems. And so to do this, we need to solve constraint satisfaction problems. And this is actually very, very close to solving optimization problems, so we also solve optimization problems. So we can solve differential equations, algebraic equations, optimization problems, and then we also need to look at operations on functions like composition, like the range of functions. And then, because all these operations can be expressed just in terms of functions over box domains, it turns out this will be enough. So the calculus of functions over box domains, this will be enough to solve our hybrid system problems. And then, of course, if we want to do this in practice, we need to do this efficiently, and because we want to verify all this has to be absolutely rigorous. So, before we go to functions, I want to first look at numbers. And this, what I'm going to say, is essentially what is probably known to all of you as interval arithmetic. I don't call it interval arithmetic in Ariadne for reasons which I'll briefly explain later. But I want to first relate interval arithmetic to a slightly higher question, which is, in the end, we want to work with real numbers. Our models, these talk about mathematical real numbers, and so we'd like to have ways of talking about and working with real numbers in a computational setting. And first, we need to have some idea of what is a real number. Well, if you think about mathematical analysis, you'll notice that the main definition is in terms of cuts. There are also definitions in terms of Cauchy sequences, and these, turns out, are the two main conceptual definitions. And we can make these effective, so we can make these into things we can compute with. If we say a real number is some object for which we can either extract arbitrary accurate bounds, lower and upper bounds for the number, and this corresponds to the Dedekind cuts framework, where you give a lower cut and an upper cut. Or we can extract, say, a rational or a dyadic rational to a given accuracy, which gives a ball around the value of interest, and this relates to the Cauchy concept of it. One thing that's important is that, given a real number, we need to extract bounds. It doesn't suffice to extract a convergent sequence, because if we just have a convergent sequence with no knowledge of how fast it converges, then from any given part of that sequence, we can't tell anything about the number. So we want to extract bounds, and we want to be able to, from a real number, we can extract intervals, and we should be able to extract an interval of which is arbitrarily small, so we can get arbitrary accurate intervals for a given real number. Once we have such an interval, then we can compute with it in a concrete way. So, given an interval of rational numbers, or dyadics, or floating point numbers, we can then do arithmetic on it just by looking at pointwise operations, possibly with outward rounding. And in fact, we can develop a full calculus of real numbers just in terms of this interval arithmetic with arbitrary precision numbers. But the thing is, once we've extracted bounds for a number, there's no way back. So we can't get back to arbitrary accuracy. So in some ways, if we want to work with real numbers as conceptual objects, well, we can do arbitrary, finitely accurate computations. If that's not good enough for whatever purpose, we may just have to go back to our original symbolic definition and then recompute with more accuracy. And this means that, well, especially in Ariadne, as well as these effective real numbers for which we can get arbitrary accurate computations, we also have concepts of validated real numbers. And this is an object for which we can compute bounds. So we can work with it using interval methods, but we can't do this for arbitrary accuracy. So we've lost some information about the number, but we still have enough useful information to compute with. And also approximate numbers. This is when we just have an approximation. We say the number is roughly 2, but we have no idea how good this approximation is. This can be useful even in the context of rigorous calculations for bootstrapping for methods, but in the end we need to go to validated and effective numbers in order to get rigorous results. So then, this is the basic theoretical framework. To implement this, then, well, we can consider a type of generic real numbers based on abstract operations. So in C++, we'd have virtual functions. For example, for a real number, we can get it to a given accuracy, and that will give us a ball whose center is a dyadic number, and maybe whose radius is 2 to the power something. So this is how we could expect it as C++ signature, or we could get bounds, and here I'm saying get with a given effort, and this says if we put a certain amount of work in, we get a certain accuracy. We're not guaranteeing how much accuracy we get for a given amount of work, but the more work we put in to the computation, the better the accuracy, and in the end, we can get arbitrary accuracy. On the other hand, in practice, we generally want to work with double multiple precision floating point numbers, such as implemented in NBFR, and then we'd maybe get a number to a given precision instead, and give bounds with multiple precision floating point objects. Now, the reason why here I've called what we're getting bounds rather than intervals is simply because in Ariadne we reserve interval for something that's genuinely a set of numbers and not an approximation to a single number. And conceptually, there's a difference between thinking about, we have a number, we don't know exactly what it is, but we know it's in some interval, and we have a set. For example, the set might be the domain of a function, which is itself an interval. And in Ariadne, we use interval purely for sets of numbers, and so we have to use some other name for single numbers. And here we call bounds and bors, which I think are fairly clear. But essentially, here what we're doing really is what's traditionally called interval arithmetic. So this is how we do things for numbers. For functions, then we want to do a similar thing. So the first aim is to develop a calculus for continuous real functions. And again, we're going to distinguish between effective, validated, and approximate objects. So an effective function will be one for which you have enough information to evaluate it arbitrarily accurately. A validated function is one for which we have enough information to evaluate it with given bounds, but not arbitrarily accurately. And approximation functions, well, these we don't have any guarantees on the accuracy, but maybe it's useful for preconditioning or in other cases. And again, we're going to use abstract types, so abstract real function types, which will define things like interfaces or for interchange between different parts of the calculation, and then concrete objects for which we really do calculations with. And then we're going to implement the basic computable operations, both at the abstract level, generally symbolically, and at concrete level. And the main operations we want to look at are things like evaluation. So given a function and a number, we can compute f of x. Any pointwise operation, in particular pointwise arithmetic, or things like sine of a function, we can apply pointwise. Composition, in natural definition. And also the norm of a function, for example, supremum norm, which is maximum over a domain. In particular, this means we compute maxima and minima over domains as well. And especially, one thing we'd like for a general purpose function calculus is we want to be able to use multiple representations in a single calculation. So we want to be able to convert from one representation to another. and then this will allow us to use to make tool chains in which we combine possibly one calculation where we use polynomial approximations, another calculation where we use Fourier approximations, and be able to mix and merge them. So then, just as for real numbers, the theoretical basis for functions, there's a well-defined computability theory which says that essentially a computable or effective real function is an object for which we can evaluate it. So given a real number, by which I mean a description of a real number, by which I mean, say, a nested sequence of intervals converging to it, we can compute f of x, and again, a description of that, or a nested sequence of intervals converging. So functions are defined by evaluation. However, one particularly nice way of representing this is by interval extensions. So given a set of real number bounds or intervals, we say an interval extension for a function is a function on these intervals, and first of all it has to respect the inclusion properties, so our interval extension on an interval contains all points of the original function evaluation on that interval, and then also for an effective or for an arbitrary accurate approximations, we need to say that if some intervals converge down to a single point, then the interval extension applied to those intervals also converges down to a single point, which has to be the image. So these are very natural. Probably a lot of you have seen this before. If we want to validate a version of the function, then we just remove this condition, so we don't require we can compute arbitrarily. And this suggests an interface which actually works for both effective and validated functions, where we can evaluate functions, say, on dyadic bounds for a number, and get dyadic bounds. We could also do things for floating point bounds, double precision bounds, which is useful if you want to do fast calculations. And in fact, for Ariadne, this is roughly what we do, except we apply, at the moment, we apply them just for floating points, either double or multiple precision bounds. However, in order to work with functions in a concrete way, well, the definition above basically will give us symbolic operations. So if we add two functions, we say, well, we evaluate one, evaluate the other, add the interval results. If we want to work with functions first-class objects, then we probably want to have more concrete representations of functions. And most of the time here, we can only directly do this over bounded domains. For example, if we want to approximate by polynomials, then we have uniform approximation over bounded domains. So call these things function patches in Ariadne, and the basic approximation classes are approximations over coordinates aligned boxes, and then typically we do things with respect to some norm, for example, the uniform. So one way of doing this is by what's called Taylor models, and this is the main thing we've implemented in Ariadne. It was originally defined by Makino and Burrs between 1999 and 2003, and essentially these are polynomial approximations, but these are scaled to the uniform domain, and this makes a lot of the function approximations much more, or the operations much more efficient to do. In particular, if we have small terms in our polynomials, we can very easily get rid of them. So then, how do we use this to look at hybrid systems? Well, in Ariadne, which is a tool for reachability analysis and verification, it's implemented in C++, and it has a Python scripting interface. And it's split into a bunch of modules. The main module, well, we have a function module where we implement the function calculus. Then we have the solver module where we can have methods for basic solution of things like algebraic differential equations, feasibility and optimization problems. And then dynamics module where we can use these for studying dynamical systems, and we have a separate module for hybrid systems. So then if we want to look at the continuous evolution, then, well, there are a number of ways of computing the flow. We've implemented two main ways. One is by looking at the Picard operator, which is essentially saying the flow of the differential equation satisfies this integral equation. We can iterate this integral equation over a small enough time steps and get a contraction system. This is once you have a function calculus, then this is very, very, very fast, very easy to do in code. Unfortunately, it turns out that it's not quite as efficient as trying to compute the Taylor expansion and look at error terms of Taylor expansion. So we also do this, and it turns out this is faster. Then if we want to look at the event detection, so we want to compute crossing times in our hybrid system, then we have to solve parameterized algebraic equations where this is the guard for the crossing and this is the flow, and we have to find the crossing time tau. So this is essentially solving an implicit function theorem problem. We've got two methods for this in our Calculi, one based on the integral Newton operator, one based on the Crawchik operator. In practice, the Crawchik operator is easier to implement and generally more reliable, but the integral Newton operator, when it works, tends to be more efficient. So then putting this all together, if we want to look at the reachable sets of hybrid systems, we can describe these in terms of flows, crossing times, and resets. And we can get some descriptions like this, which look very complicated, but these all fall into the class of what I call constrained image sets. So we take some parameter domain, take a box and parameter space, map it forward to get the set of points we're interested in, but we also restrict the set of parameters we look at. So we have a description like this. And once we have this description, then computing the image under a function and intersecting with other sets we can do just in terms of composition of functions. So we can reduce geometry to our function vectors. And then to perform safety verification, we essentially need to take these sets and check whether they intersect other sets, for example, with boxes. And to do this, there are a number of, this is basically non-linear feasibility problem, and we can do this using a number of techniques. The main technique we use are to use, we try and solve the problem using primary geo methods with Lyapunov multipliers. If we find a solution, that's great. If we don't find a solution, then we can use the multipliers in various contractors like hull reduce or box reduce to try and prove no solution exists. And if all else fails, we split into smaller pieces and try again. But essentially, all these operations we can do by combining operations on function terms. So as a brief example, we've looked at a very simple water tank system where water comes in and we have to control the height using a valve which has a slow opening and closing. This is what it looks like as a hybrid automaton, and this is what we can compute with Ariadne. This is a very simple computation. If we want to prove things about it, we can also discretize on a grid and try and prove properties. But these are very tight flow tubes around the system dynamics. So going beyond hybrid systems, well, there are many things we could do. Here's some technical details on how you could do function calculi in Fourier spaces and use them for partial differential equations. There's been some work in this area involving Konstantin Mishaikov on some discrete time and continuous time models. But while they can solve particular problems, they haven't developed a really general function calculus in order to be able to do these fairly automatically. And there are many other kinds of function calculi one could use for different purposes. For example, as well as Taylor bases for continuous functions, one could use Bernstein and Chebyshev bases, and there are packages that do this. You can use Fourier bases for signal processing, Sobolev spaces for PDEs, finite elements and spline functions again for PDEs. I think one particularly interesting thing to do is to look at exponential polynomial functions or subsystems of ODEs, and piecewise continuous functions or piecewise constant functions for things like Bank control. And just to summarize, so I've shown a basic outline of how we develop a rigorous calculus for working with continuous functions. We base it on computability theory for a clean foundation and provide many different implementations for different purposes. and we've implemented these in a software tool, Ariadne, for reachability analysis of hybrid systems. There are many, many directions for future work. For me, I think actually the most important is to improve the cleanliness and efficiency and documentation of Ariadne, and really to try and attract users, because so we have a lot of functionality. It sometimes feels like it's a bit all cobbled together, and having people that start to use the tool and see what their experiences are will really give us help in terms of which directions to improve. So that's all, and thanks very much.
So any questions? Nassim?
I have maybe a couple of questions. Maybe first question quite in detail. In slide 20, you say, my understanding is that you use the Newton operator.
Yeah. 20.
Maybe prior. Yeah, this one.
Yeah.
Somewhere.
Yeah.
But the algebraic equation is kind of Piston square, isn't it? Is it? I mean, I guess the Newton operator. The function g is from a Rn to R.
Yes.
So I wonder how you could use the Newton operator on such.
Right. Okay. So here I've deliberately given just the equations for solving a single algebraic equation rather than parameterized algebraic equations. The way you do it for parameterized algebraic equations is, well, in some ways you have to bound the derivative at all points, and you can either try and bound the derivative at all parameter values, or you can try and parameterize integral derivative. I think what we do for it's been a long time since I've worked on this, so I can't actually understand what we do, but I think what we do because when computing the crossing time, we're only got a one-dimensional problem to solve, we can actually parameterize the integral derivative values.
Okay, so you kind of solve it in one direction at a time.
But here we only have one direction to solve, which makes it easy.
No, because I just encountered this kind of problem, so I was wondering whether you could find a recipe to use something.
But there are lots of things you can do. I mean,
and then maybe a general question. There have been quite a huge amount of work in reachability computation with general hybrid systems, and I wonder how your contribution stands with respect to the different tools and theories that exist. Can you comment on this, please?
So in terms of the tools, I think the closest tools that I know are Checkmate, Hypertech, which was a non-linear interval extension to Hytech. It's quite old, but it doesn't, as far as I know, have very general nonlinear functions. So we go much further in terms of nonlinear guards and nonlinear functions. Another tool which is fairly similar to ours and also uses Taylor models to compute closure differential equations is FlowStar. There, I think, in terms of their continuous evolution and crossing, they can do pretty much the same as we can. Their crossing detection, they have a much simpler engine. So they, for example, I believe they can't solve the algebraic equations for crossing times, but they have some tricks that they can do, like recombining sets, which we don't influence at the moment, which mean that they don't have to solve the algebraic equations for crossing times. But they have a fairly similar kind of calculus to Ariadne, and I think what they do is they might do slightly better, but they don't do as much. In particular, they can only compute flow tubes, and they can't then discretize. They can't do global reachability analysis or reachability verification. There are plenty of tools each with their own abilities.
It's a quite strong comment you're making there. Just make sure that there has been some work that has been published in verification conferences and they are indeed using state-of-the-art tools. So I encourage you to have a look to these papers and see how your contribution stands.
But I mean, we've been working on this for a long time, so we've obviously tried, from time to time, we try and keep up on what's the state of the art.
Okay.
Was a question?